Okay, students, during last lecture, we started virtual memory. Okay, we started to study about virtual memory concepts. Okay, the virtual memory concepts the complete program will not be saved in the main memory. Okay, so in a virtual memory, the complete program will not be saved in the main memory, will not come to main memory during the execution. Okay. So either the program will be splitted into fixed partitions, or the program will be splitted into varying partitions. Okay. So based on this two, splitting the program into fixed partitions to store in the main memory, or splitting the program into varying sized uh, partitions to store in the main memory. Based on this two method, there are two virtual memory management techniques. There are two virtual memory management techniques. One is paging, another one is called segmentation. Okay. Paging already I started, but I repeat. Okay. Paging and segmentation are virtual memory management concept. Okay. And one more thing, in paging and segmentation, what is the why how what is the reason actually we splitted the program into different partitions? Why not in the prior techniques, prior memory management techniques, we did not split the program into different partitions, and now we splitted? Because when execution of any program happens, the entire program is not needed to store in the main memory. Okay. Anyway, any particular statement or any particular combination of statement only will be executed. Okay. So why honestly the entire program should be stored in the main memory, and that will also, if entire program is stored in the main memory, few programs only participate in the multi-programming system. Okay. So we split the program into partitions, either fixed size or varying size. Based on that, there are two virtual memory management techniques. One is paging, another one is segmentation. Okay. In these two techniques, when we store the data, when we store pages or segments in the main memory, we will not store sequentially. We will not store sequentially. Okay. Contiguously, we will not store. We will store non-contiguously. This is another important point you have to remember. In these two techniques, whenever we store the data in the main memory by following any one of these data sequentially. That means a first partition and the continuation of the second partition will be in the next address, and the continuation of that will be in the next address. It will not be stored like this. Continuously, we will not store. Okay. The splitted programs, different segment you will see in different places of main memory. Okay. Different places of main memory. So these two techniques will come under non-contiguous memory allocation for the processes. Non-contiguous memory allocation. Okay. So the partitions will not be allocated in the main memory contiguously. Okay. It will be allocated non-contiguously. Okay. So these two techniques are non-contiguous techniques. Okay. Now first, what is paging? Paging is a method, or you can say paging is a technique which is used for non-contiguous memory allocation. Note down, which is used for non-contiguous memory allocation. Here, the entire main memory will be split into different partitions, and the secondary memory, which is virtual memory, will also be split into different partitions. Okay. But all the partitions are fixed in size. All the size of the partitions are same. Okay, in paging. Okay. The sizes of the pages are same. All the frame size also same, and the frame size as well as page size is also equal. Okay. So this, if suppose this is 1 KB, all these, every frames are 1 KB frames only. And of course, the page will also be 1 KB page. Fixed size partition. Paging is fixed size partition. Okay. What is this? This is secondary memory. Where actually page is there, no? That is called a secondary memory. Secondary memory, here we have to say the secondary memory as virtual memory. Okay. So virtual memory is split into fixed size partitions called pages. Secondary memory is split into fixed size partitions called pages. Okay. Main memory is also also divided into fixed size partitions. Those partitions are called frames. Main memory frames, secondary memory pages. Main memory frames, secondary memory pages. Okay. Now, why this is needed? When any page, okay, when we are taking from the secondary memory to store it in the main memory, okay, any page when we are taking from the secondary memory to store it in the main memory, okay, where we have to store this secondary memory page into main memory. Where, in which location? There are many locations, no? This is non-contiguous allocation. So first segment will be stored, second segment will be stored here. It will not be like that. Okay, non-contiguous allocation. Okay. So when non-contiguous allocation, then when the MMU, memory management unit, bringing the page to store it in the main memory, it has to know that where it should be stored. Okay. So when MMU is bringing the page from the secondary memory to main memory, it will already know that the address of the secondary memory from where it has taken the page. Okay. But when it is storing in the main memory, it has to know where it should be stored. Okay. So where it should be stored in some address location only, of course. Okay. So changing the logical address into physical address is called paging. Changing the logical address. That means I assume that page 2 MMU is taking to store it in the main memory. Okay. So page 2 here in the secondary memory, it will be stored in some address. Okay. That address is called a logical address. Okay. In the secondary memory, addresses are called logical addresses. Okay. So the page 2 I want to take, MMU wants to take and keep it inside the main memory. So MMU knows the address of the page 2. Okay. In the secondary memory. Now it has to know where here, in which address it has to store the page 2 here in the main memory. Okay. For that, there will be a address conversion. The MMU will do address conversion, memory management unit. Okay. MMU will do that conversion is called uh, paging, or we can call logical address to physical address conversion. Okay. Logical address to physical address conversion. Okay. The addresses which are there in the main secondary memory, addresses which are there in the secondary memory are called logical addresses. The addresses which are there in the main memory are called as physical addresses. Physical addresses main memory, logical addresses secondary memory. Okay. So that how that address conversion will happen. Okay. How that address conversion will happen, we will see in another diagram. Now, before understanding that, you have to know this. Okay. Now, CPU knows the, because this only access directly disk, no. Okay. So, when it is executing the program from the disk only, that means the virtual memory only, the data will come to CPU. Okay. That's why generally we will say CPU will create the logical address. Okay. CPU will create the logical address. You know what is logical address? Logical address is the address. It will be there in the secondary memory, virtual memory. Okay. So assume that this is one logical address. Okay. This is one logical address. So this logical address has two different segments. Okay. or two different parts, you can say. Okay, one is called page number, because page will be there in the virtual memory, secondary memory, no. So one part of the address will have page number, the another part will have offset. Okay, offset is nothing but the address. Suppose one page is a 4 KB page. Okay, so that 4 KB page we will not denote using single address, right? Okay, inside the 4 KB page we will have many addresses. Okay, to denote each and every byte of data in a 4 KB page, we will have many addresses. Okay, so after we found which page, inside the page exactly where the content is. Okay, so that address is called offset. Okay, here they have given D because this is generally called displacement. Okay, we will call this as a offset, OFFSET, offset. Okay, so this is one address, and this address is a address inside this address inside this address. Okay, this is the page address, but within the page exactly which byte of data I am going to access, that byte ka address will be there here in the offset. Both are addresses only, remember. Page number is also address. Okay, and this displacement or offset is also address. Okay, okay. Now logical address will have two part. One is page number, another is displacement or otherwise offset. Okay, now our MMU will receive this. Now what is the work of the MMU? This particular content, page content, should be loaded in the main memory. It has to find in which location it has to store this content in the main memory. Okay, so that there will be a need of address conversion from the logical address to physical address. Okay, if it converted, then only we will get a physical address. Then we can look into the physical address to store this page content. Okay. So these are the two parts in the logical address. Okay. Now MMU should find the physical address, equivalent physical address of this logical address, where the logical address will be in the virtual memory. Remember. Okay. Because in the virtual memory only we have pages. That's why here it is page number. Okay. Okay. Now MMU we have a table called page table. When it will be created whenever the process created. Okay. Whenever process created, page table will be created. The page table will be stored inside the address space of this process. The page table will be stored in the address space. You know, whenever a process is created, simultaneously process ID and all the related information to the page will be created. Okay. So all these information related to single process will be stored where? In an address space. Okay. Where the address space will be there in main memory. Okay. So where the page table would be, then page table will also be inside the main memory, not in the secondary memory. Page table is a reference table. Okay. So this table, one table will belong to one process only. How? One address space will belong to only one process, like that. One process, per process, one what? One page table. Okay. So in any address space, if you look into, you can find the page table. Page table, when it will be created, when the process created, it will be created. After created the process address space. Okay. Inside the address space, this will be created. Page table. Okay. Now, what will be the content of the page table? This page table will have page numbers here. For example, assume that the current process, that process will be related to one program, right? That program is divided into 6 number of pages. Okay. So here then how many number of page numbers will come? 6 page numbers will come. Okay. So number of page numbers is depending on how many number of pages the program is splitted. The program is splitted into how many number of pages. Okay. So assume that there are 6 pages. So page 1, page 2, page 3, page 4, page 5 will be, this is page table. So here page number will be sequence. Remember, this is a reference table. Here page numbers will be sequence. Okay. Assume that here the page number is 3. Okay. This in a logical address, there will be a page number. No, the page number is 3. So where we have to find page 3 here. That is easy in a page table because the page numbers are sequence. Okay. So assume that here I find the page 3. Now inside the page 3, what is stored in the page table? That will be C. Okay. So inside the page 3, there will be a frame number, page frame number. Okay, page frame number. Please understand, frames are there in the main memory. Pages are there in the secondary memory. So the page table will have page numbers, and inside the respective page number, its respective frame number will be stored. Okay, so this is a reference table. Okay, now which page came now? Page number 3. So here assume that here page number 3, we found that page number 3 is stored in frame number 8. Okay, so here I have written F no there. So I did not write, it is written here F no there, I assume that 8. Okay, so page number 3 ka respective frame number is what? 8. So this is the, now what MMU is doing, it is forming the physical address. It is forming the physical address. When it is forming the physical address, one part it found with the help of the page table. One part of the physical address it found with the help of the page table. How? In the logical address, there was a page number. That page number, it look into the MMU, look into the page table. And inside that particular page number, it found that its respective frame number. That frame number going to be the first part of the physical address. Okay. So we found the page numbers, frame number. Now, inside the frame here, frame, assume that the frame is 4 KB frame. Okay. So inside the frame also we have to find exactly which byte the processor related to. Okay. So this address is same as this address. What is the address you're writing here? No, it is given here, CPU given here, the same address will go here. No conversion. How? Can anyone say how these two offset can be same? How? Let me see. See, this page number is different from this frame number. Okay. But this displacement number is same as this displacement number. You have to just take this number. For example, this is 10-bit number. Okay, 10-digit number, binary number. So the same 10-digit binary number will come here as an address. How? Can anyone? I just want to check whether you're listening or not. Sweetie, anybody? Hemakshi, Glory, Ajil, Kaifali. Let me see who's saying. Aishwarya, Ajil. Students, are you all there? Are you all listening?
Yes, ma'am.
Yes, ma'am.
Can anyone say how both the offset of logical address, offset of physical address, both are same? How? I said what is offset also, no? Then you should able to say immediately. This is offset. Here also this is offset. So this is one of the addresses inside the complete page. Page is what? Page is assume 4 KB page. Okay. So in 4 KB page may exactly where the content is. Okay, so address of that is this offset. How this and this could be same? Yes, fast. Yes, students, what happened? Not listening?
No, ma'am. Sundar, I'm listening.
Sorry, I couldn't hear. Supreet, you said something.
नहीं मैम कुछ नहीं बोला.
Yes, yes, fast.
Because they share the same page number.
How sharing the same page number means I did not get. Sharing the same, where it is sharing the same page. See, page number will be definitely different than the frame number, remember. Otherwise, we no need to have the page table, no. When page number and the frame number both are same, then we no need to have this page table as a reference, right? What the page table will have page numbers sequentially, and inside that its respective frame number. For example, page 1. Assume that page 1 is here. Okay, here page 2, page 3, page 4, page 5, page 6. Okay. So page 5, assume that it is stored in frame number 6. Okay. Page 2 could be stored in any page number 10, 11, or even 1, anywhere it can be stored. Okay. So page number, suppose you should not think page number 1 will be stored in frame number 1. Then the entire concept is not required only. Okay, page number 1 will not be stored in frame number 1. Why? Why? Because main size of the main memory and size of the virtual memory is not same. Right? Size of the main memory and size of the secondary memory, virtual memory is not same, no? Then how exactly page 1 can be stored in frame 1? No, definitely not. That is one point. And another one, if that it is like that, then there is no need of this paging, segmentation and all. Easily we can refer, okay, page number, frame number 1, page number 2, frame number 2. There is no need of reference table, no need of the paging concept only. Okay. But here the allocation, that's what I said. These two techniques are example for non-contiguous allocation. Non-contiguous allocation. That means in the main memory, page number 1. I should not say page number here because it's frame number. Okay, but just to understand, I'm saying page number 1 is stored here. Page number 2 will be stored here. Page number 3 will be here. Page number 5 can be here. Like that, it will be stored randomly. Okay. Why randomly? Because wherever the free space is there, there it will load. Wherever in the main memory free space is there, then only the newly brought page will be stored in the frame. Okay. So it will not, it is not a contiguous allocation of data inside the main memory. Remember. Now you tell me page number, assume that a program is splitted into 6 pages. Okay. Page 3 I want to refer. So here it is page 3. But remember page in it will be there in a binary format, all the addresses, everything. Okay. Just to understanding, I'm saying this is page number 3. Okay. So in the address, logical address, page number 3 is there. Okay. So page number 3, to find this frame number, it has to refer the page table. Okay. To find the equivalent frame number of this page number, we need to refer, MMU need to refer the page table. Okay. So page number 3, assume that here the page number 3 is there. So inside the page number 3, what is the frame number here? The frame number will be there. So that frame number will be will come here as a part of the physical address. Okay. Now off part of the physical address has been framed. Okay. Another part should be framed. Then only the MMU can go and store the page exactly, page data into the respective frame. Okay. So what is this number? I said how it will be framed also. Here to form the frame number, there was a reference required. Okay. But here this to find the offset of the physical address, there is no conversion required. Okay. Exactly here, for example, it is assume that it is 28. Here also it will be 28. If it is 28 here also it will be 28. But here it is 3, here it could be what? Any other number. Why? I am asking why these two numbers will be same. Simple. Students, simple. Very simple question. Anybody? Why offset is equal in the logical address as well as physical address? Very simple. Okay, nobody is ready to think, right? See, again and again I'm saying page size is equal to frame size. Size. Suppose this is 4 KB and this also 4 KB. Okay. This is 4 KB. This is also 4 KB. Okay. So when here also it is 4 KB data, the same data only we are going to load in the frame. So inside the data, the content will not be changed, sequence will not be changed. Okay. Here also 4 KB data, here also 4 KB data. So 4 KB data ka first byte mein what content was here, the same content will be there here also in the same first byte. Okay. So inside the page what we want to refer or inside the frame what we want to refer will not vary. Okay. Suppose page number 3 mein, inside page number 3, I want to refer byte number 28. Byte number 28. Okay. Of course, frame number will vary. Okay. But how the offset inner content will vary because the same data only we are storing here, right? This is also 4 KB data, the same 4 KB data in the different frame together. Okay. So here first byte, here is also first byte. Here second byte, here also it will be second byte. Remember. Okay. Okay. Now I think you will clearly understand, but you have to listen very carefully. You have to listen. No distraction. Okay. You have to concentrate here. This is a conversion of logical address to physical address in paging. Conversion of logical address to physical address in paging. Assume that this is the logical address. Here what they have given is the size of the address. Okay, so the total size of the address page, the logical address is, total size of the logical address is what? 13 bits. 10 plus 3. 13 bits. Okay. In that first 3 bits denote page number. Next 10 bits denotes offset. Okay. Okay. Here there is a physical address. Assume that it is a 12-bit address. Okay. You can guess why it is lesser than the logical address, because logical address where it will be in a secondary memory. Secondary memory is bigger than the main memory. Okay. So address size will also vary accordingly, right? Okay. That's why. So now here displacement is how many bits? 10 bits. Here also it is 10 bits because same data. Here there will not be offset. Size of the offset in a logical address and physical address will not vary. Size of the address. But size of the page number in logical address and frame number in physical address will definitely vary. Size. Here it is not the actual number, it is size of the frame number and page number in the logical address and the physical address. Okay. You know, I said the reason why here 3 bits, here 2 bits, because this is small memory, this is large memory. Okay. So size of the address will vary, right? Isn't it? Very simple. There are 2 houses. Students, there are 2 houses. Okay. You want to represent the house number using minimum number of digits, binary digits. Okay. Only 2 houses. Okay. How many number of bits you need? How many number of bits in the address is needed? Only 1 bit is enough, no? Because 1 bit may you can store 0 or 1. So one house number will be 0, another house number will be 1, right? Isn't it? So how many bits you want? What is the size of the bit? Only 1 bit. Using 1 bit, 2 different things you can denote, right? Okay. There are 4 houses. There are 4 houses. Okay. Only 1 bit is enough to denote its number? No. Because using 1 bit, 0 or 1 only you can denote. That means using 1 bit, 2 different things you can denote, not more than that. Okay. If 4 houses are there, to denote its addresses, we need 2 bits. Okay. Why? Using 2 bits, how many combination of addresses we can create? Using 2 bits, how many combination of addresses we can create? 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 is one house number. 0, 1 will be another house number. 1, 0 would be the third house number. 1, 1 will be the fourth house number. So using 2 bits, 4 houses we denote. Okay. So now the number of digits, number of binary digits required to represent the house number is depending on what? Depending on what? Depending on number of houses. Okay. So can we represent the house number using 2 bits when more than 4 houses are there? No, it is not possible. Then we have to go to 3-bit address. Okay. The same way here, this is a small memory where they did not give 2 memory. Okay. This is the large memory. What is this? This is secondary memory. Logical address is secondary memory. No, so page number is larger than the frame number, because number of frames will be always less than number of pages, because this is small memory, this is large memory. So to represent small memory, we need very less number of bits of address. To denote large addresses, large memory, we need more number of addresses. Okay, that is why. Okay. Okay. Now this is the logical address and this is the physical address. Okay. Now logical address will be taken and it will be referred inside the, what is this called, a page table. Okay. So assume that page number 3, and inside the page number 3, page number 2, not page number, frame number 2 is there. Okay. So by taking that, that is what it is taken from here is called frame number. Okay. So that frame number will go here. That frame number will go here to frame the frame number inside the physical address, and this bit will be exactly will go to complete the second part of the physical address. Okay. Here we in the diagram it is shown. See now which frame number is 2? No, frame number 2. So here these are what frame numbers. So frame number 2. Okay, frame number 2. Here exactly we have to store the page number 3 content, no, that we have to store inside this frame number 2. But when we are storing the data, see, as a lines, there are many addresses will be there. This is one address inside page 2, and this is another address inside page 2. Each and every address will denote 8 bits. That means 1 byte of data. Okay. So now here, if I want to refer page number 4, then the respective page, offset number will be given. So to represent these inner lines only, we need what? We need a offset. Okay. We found the frame number as 2. But inside the frame 2, which content? There are so many contents, you see. Okay, 4 bytes of data. Okay, that means so many number of bytes. So which byte exactly? To find that only we use what? Displacement or offset. Okay. Okay. So like this, the address conversion will happen. After MMU converted the address, it will aram se store the data inside the main memory in the form of frames. In the form of frame. Okay. Next is called next technique or next method also you can say. Next method is called segmentation. Okay. Segmentation is another non-contiguous virtual memory allocation system. Segmentation is another system. Let me show the diagram first. Simple diagram and then address conversion we will see here. Okay. This is segmentation. Okay. Here this is also non-contiguous memory allocation technique. Non-contiguous memory allocation technique. That means inside the main memory, the segments will not be stored sequentially. Okay, it will stored randomly wherever the space is there. Okay, but the difference between paging and segmentation is in the paging, the single program will be splitted into fixed size partitions. Fixed size. Okay, page 1 is 4 KB, page 2 will not be 4, will also be 4 KB, page 3, 4, 5, whatever pages are there, all the pages size will be 4 KB only. That's why it is fixed size partitions. Okay. Here it is varying size partition. Varying size partition. Okay. Assume that this is a single program. The program segment 0 is splitted like this. Segment 1 is little bigger than the segment 0. And then segment 2, segment 3, segment 4. See, these are different sizes. But all these segments are belonging to single program. You have to remember that. All these are belonging to single program. Okay. Why the segment there be splitted into fixed size partition, here varying size partition? Because in fixed size partition, we create when we split into fixed size partition, what will happen? Internal fragmentation will happen. Internal fragmentation will happen. Where internal fragmentation will happen? For example, I am talking about the disadvantage of paging. Paging. This diagram is segmentation diagram. Okay. I am talking about the disadvantage of paging. Okay. Assume that in paging here like this, there are 5 pages. Okay. But there are fixed size. Those pages are fixed size, same size. Okay. Okay. Now the program is splitted into many 4 number of what? 0 to 4. That means 5 pages. The last page is what? Last portion of the last segment of the program, right? Last page will be the last segment of the single program. Okay. Last segment we can't fill the entire page. Okay. Assume that there are 25 lines of code. 23 lines of code. 23 lines of code. Okay. So first 5 lines will be here. Paging may fixed. Okay, fixed size. First 5 lines, second 5 lines, third 5 lines, fourth 5 lines, 20 lines of code got over. Okay. Last page may only 3 lines of code will be loaded. But 5 lines of code you can store. Okay. So internally, that means internal to the page, there will be a free space that is called the internal fragmentation. Okay. Inside the page, there will be a unused free space. There will be unused free space in paging. Okay. there the another page content cannot be loaded. Okay, you know, because one page content should go to one frame number, one particular frame number. Okay, you can't merge two pages content and put it in a main memory. That is not possible. Okay, so when next program stores, this particular space will be wasted as it is, will not be used by any other process, and the new page will start. Okay, so internal fragmentation will happen. That is the main disadvantage of paging. This will come definitely. Okay, disadvantage of paging method, paging memory management method is what? Internal fragmentation. Why it is internal fragmentation? Internal to what? Internal to the page. Inside the page, there will be unused free space, that is called internal fragmentation. Okay. Okay. So now to avoid that only, we are splitting. And one more thing, the reason for segmentation is, when we see the program, for example, 10 lines of program, okay, 10 lines of program may assume that 4 lines are if statement, okay, if else statement. So when paging may, what will happen? When we are splitting into fixed size, one part of the if loop will go to one page, another part of the if loop may go to another page. If loop to one code segment, no, that should not be splitted. Okay, that is a single statement. Okay, but it is a conditional statement. That means that's why it has more number of lines. Okay, so one half of the if loop will go to one page, another half of the if loop may come to another page. So there is no meaningful partition, where in paging there will, if you look at the inside content, there will not be meaningful partition in paging, because the condition is what? Always fixed size partition. Okay, but here in segmentation it is not like that. Inside every segment, if you look at the content, that those are related content. All the related content will be in one segment. Next, for example, one function ka definition. So the function logic will be there in the one segment. Okay, that logic will not be splitted into two, and one will go to segment 2, one will come to segment 3. That will not happen in the segmentation. So inner content of the segments are meaningful content. Okay, but inner content of the pages are not meaningful content. Okay, that is another one you have to remember. Okay, now we will see, this is the logical address space. Okay, which means inside the secondary memory, inside the virtual memory, the segments are stored like this, sequentially. Segment 0, segment 1, segment 2, segment 3, segment 4, but there are varying size segments. Okay, like page table. In paging we had page table. Like that, here we have segment table. Okay, in segmentation we have segment table, but the content of the segment table is completely different. Okay, here of course, like page table may how page numbers were there, the same way here segments number will be there. Okay, segment 0, segment 1, segment 2, segment 3, segment 4. Here also segment 0 to 4. Okay, this is a segment table. Okay, so segment numbers would be there. Okay, and segment number, and inside, if you look at the inside the segment number, inside the segment table, you will find base address of that segment. For example, segment 0's starting address of the segment 0 is 500. Okay, not here in the main memory. Okay, because you remember in page table, here page numbers were there. Inside the page number we had frame number. Okay, where the frames will be inside the main memory, no. So inner content of the table will have the information of main memory, not the secondary memory. Secondary memory ka content to idhar hai, here. These are secondary memory content. Okay, so these are the segments which are there, segments numbers sequentially stored in the disk. But these are addresses which are there in the memory, main memory. Okay, Okay. Now in the main memory, segment 0 is stored here. Okay. Its base address is 500. That's what given here. Base address 500. Limit is nothing but the total size of the segment. Total size of the segment. For example, how many bytes of data are there in the segment? Okay. So 500, the end address of the segment 0 is what? 1100. So 1100 minus 500 will be what? 600. That will be the size of the segment. Okay. So this segment ka size is 500 bytes. Okay. Sorry, 600 bytes. 1100 minus 500 will be 600. So that is called limit. Limit is size of the segment. Okay. Size of the segment. Which segment? Segment 0. Segment 0's base address will be 500 and its size will be 600. Okay. Like that, you look at segment 1. Segment 1 is here. See, it is not stored contiguously. Page segment 1 and segment 2 is segment 0. Segment 1 is not here. Segment 1 is somewhere else in the main memory. Okay, so it is called a contiguous allocation. Segment 0 here, segment 1 here, segment 2 here, segment 4 here, segment 3 here, like that it is. Okay, non-contiguous allocation inside the main memory. Okay, so that is base address and limit. And one more segment we will see, segment 1. Here the segment 1 is in the main memory. Okay, segment 1 may where it should be 2500 is the base address, which is the starting address of segment 1. Okay, what is the limit? 3300 is the end address of segment 1. So end address minus starting address will be the size of the segment. Okay, that is nothing but 800. Okay, if you want to know this is in which unit, it is in bytes, number of bytes. Okay, so you can assume this one line is 1 byte, second line is second byte, third line is third byte, etc. Okay, so like that, how many number of bytes are there? 800 bytes. Okay, okay, so these information will be there. Suppose here the stored structure they showed. Okay, but when you are taking the data from the secondary memory and referring the segment table, here this portion will be free. Okay, here the diagram is showing after, by referring this, after loaded all the segment, how the main memory would be. Okay, but before storing how the memory would be, it will be free. Okay, completely. Okay, so if assume that I want to store the segment 3. I want to store segment 3 inside the main memory. Assume here segment 3 not yet loaded. Assume. Okay. So segment 3 is bringing from the secondary memory, virtual memory. Okay. Where in which address it is loaded? 3 in secondary memory. So what is the segment number 3? So here, where is segment number 3 here? So MMU will search this. It will find this. Okay. Okay. 3 is a segment number. And segment number 3 should be stored where? In a base address 4600. Okay. So base address 4600 may it will load the segment 3. Okay. What is the length? Length of the segment? Length of the segment is what? 200. So it knows that 200 bytes it should be load. Okay, it loaded. Like this, the data will be go from the secondary memory to main memory whenever that particular segment is being executed by the CPU. Okay. Why segment by segment it is going? Because main memory may space is very less. Okay. Students, one more thing you have to remember. One more thing. In this example, we have shown simply one program. Only one program ka segments we have shown. Okay. But in a multi-processing system, key in your ears, listen properly. But in a multi-processing system like this, so many programs will be splitted into many segments. All those segments will be loaded in the same main memory scatteredly. Okay. So to refer those segments, so this is the segment table of one program, this program, segment table of this program. Okay. For next program in the multi-processing system, there will be another segment table in that program's address space. Okay, there will be another segment table. Okay, so when any segment of that program should be brought to main memory, the MMU will refer that table, that process ka table. Remember, here for simplicity, we have shown only one program ka segments, how it is loaded. But in a multi-programming system, there would be more number of programs, no? So all those will be loaded, and you then imagine what is the function of the MMU, how it has to, what, the address conversion or how it has to do. Okay. Okay. So this is called a segmentation. In the segmentation, what is the disadvantage? Of course, segmentation is also having disadvantage. Though it has many advantages, segmentation is also having disadvantage. What is that called? That is called external fragmentation. That is called external fragmentation. What is external fragmentation? External, when I'm saying word external, it is external to segment. External to segment, out of the segment. Okay. How when I was saying about internal segmentation in paging, it is inside the page. It is inside the page. Here when I'm saying external segmentation, it is outside the segment. Here we are talking about segment, no, not about page. So it is external to the segment. Okay. Now segment 1, 0 is loaded here. Okay. Segment 2 is loaded here, 3, 1 loaded here, like this. Okay. Assume that here, somewhere here, there is a small space left. A small space. Okay. In that space, we can't load any segments. Okay. But that free space where it is happening, it is outside the segments, because all the segments are not in same size. No, because see, one segment is very small, one segment is very large. So randomly here and there, when I load, in between there would be a free space cannot be used by any of the segments. It could be 1 byte data, for example, 1 byte of data could be there. 1 byte data, none of the segment will have, so there nothing will be loaded. Okay, say external fragmentation may happen. Okay, external fragmentation may happen. So this is about the paging and segmentation. Okay, in the segmentation, I have to say about the address conversion. There also logical address should be converted to physical address. Why? Because the segment from the secondary memory should be loaded in the main memory, right? Okay. Here simply the address conversion will happen. Look at here, CPU gives which address? Logical address. Logical address there, there in paging, logical address had page number and offset. Here it is segmentation. So logical address will have segment number and offset. Okay, offset is what is the inner content inside the segment should be referred. Okay, so logical address of the segmentation will have segment number and offset. Okay, okay. And we already discussed about the segment table. Segment table will have the segment number sequentially, and then its respective that segment's base address and its size of the segment. Okay, okay. So now what should be formed? We have to form a physical address. Okay, MMU should form a physical address. How the physical address will be formed? You remember how logical to physical address had been formed in paging? In paging, simply the page number of the logical address will be fetched and look into the page table. It will find the respective frame number, and along with the frame number, logical address offset will be combined, and that is called a physical address. Okay, but here see the segment number, by taking MMU, by taking the segment number, it will look inside the segment table. Okay, and inside the segment table, it will find now forming the physical address I'm talking about. Okay, so it will find only the limit is size, no, limit is size. Okay, so this offset of the logical address is less than limit. Please, you have to think here. You have to think here. Offset is less than limit. Offset should be less than limit. No, for example, size of one particular segment is 500. Okay, size. So that is 500 here, 500. Okay. But offset is saying that it is 600. Okay. What is offset? Offset is something inside the segment. Offset is something inside the segment. Okay. So then how the offset can be greater than limit? It should be less than limit, no? So if it is less than limit, then both togetherly formed. That means here the outcome is what? Outcome is limit. Okay. And plus the base address will be togetherly added, and it will form the segment number in the main memory. So these segments are here in the main memory and secondary memory. Both the places this will call segment only, not like page. Paging may what? Pages will be inside the secondary memory. Frames are inside the main memory. But here inside the secondary memory also segments, and inside the physical memory also those segments, partitions are called segments only. Partitions are called segment only. So what will be added? The limit which is taken. Okay, if the limit is less than the offset, then that is correct address. Okay, so that plus the base address will be added, which will form the address where we have to store the particular segment. Okay, so that address is called physical address. Suppose this is not satisfied. That address will be that attempt, the comparison. This comparison gives the outcome no, then that address will be just ignored. That means by taking that address, the MMU will not look into the main memory. That means some error in the address. So if it's no, then it is invalid address that will be come out of the execution. Okay. So this is called segmentation. Now students, you can take a 10 minutes break, and then exactly you will join us 12:50. Okay, 12:50 you have to join again. Okay, you can leave now.
Okay, ma'am.
Ma'am,
12:50 you have to join. Yes, who called
ma'am,
me?
can you
Yes, sweetie.
upload this PDF today?
Wait, now when I'm ending your lecture, no? When I'm ending lecture, in front of you, I will upload. Okay. So then you
Okay,
can
ma'am.
take
Okay,
even
fine.
this and the previous this also. But at the end of the lecture, you remind me. Okay. I will
Okay,
upload
ma'am.
that time itself. Okay.